In a convolutional neural network, and this is often abbreviated CNN, we have a network of convolutions. So we're going to have some input, and this is our input, and I'm going to feed it through a convolution. Really, a series of a set of convolutions at this layer. So at this layer, we're going to have a certain number of convolutions, right? Often 3 by 3. If this is K, it's going to be K. And we have some set of them, let's say S. So if we've got S of these, let's just call this input height and width, what are we going to get out? We're going to get out, if we apply our convolution, each 3 by 3 by K kernel is going to give us a output, assuming half padding and 1 stride, of H by W by 1. And if we have S of these, we're going to end up with H of W by S. Now we could feed it into another convolution, right? No, we wouldn't feed this in another convolution, because if we have 2 convolutions in a row, that's just like 2 matrix multiplies in a row. It still could be replaced by a single convolution. So therefore, the next thing we do is we add in a nonlinearity. So we're going to put in a nonlinearity. Let's say it's a ReLU. What does a ReLU do? A ReLU takes us into the same H by W by S, right? Just with no negatives. Now we can go ahead and afford to apply another convolution. So we would often do another convolution here. And this might give us some H by W by some new S, let's say S prime. Okay, because we would have S prime convolutions, each 3 by 3 by S. And we then would feed this into another ReLU. We get tired of this eventually. So often what we'll have is a CNN is going to look like a convolution followed by a ReLU, and this will be repeated some number of times. So this is using kind of regular expression syntax. So we're going to repeat it 1 or more times. Convolutional neural networks often look like is that they will start out with an original size, and then we'll do some convolutions, and then we shrink the size. In fact, what commonly happens is there'll be this balance in a neural network as we go from layer to layer to layer, where the size of the inputs remains about the same. That is, as we are increasing the depth, we start decreasing the height and the width. How do we decrease this height and the width? With some sort of a pooling operation. So we do a pooling, and then what we would often get is something where we're H over 2, W over 2, still our S prime. And then, once we have shrunk the height and the width, we often will now increase the number of features, the number of kernels. What this really looks like then is we have convolutions and ReLUs, and then that is often followed by a pooling, right? Max or average pool. And that is repeated 1 or more times. And as the height and width then get smaller and smaller, the number of features often grows, and then eventually we get to some sort of an end state. Let's look at an example. So the example we're going to look at is MNIST. MNIST is a fairly famous data set. It was one of the first real uses of neural networks in industry. And what it was used for is there was a contract put out by the US Postal Service. And what happens is, right, people write, this is the stamp, this is the return address, and here we have, 92373. So we have a zip code. The desire was to have the machine read the zip code without human intervention. It used to be what happened is actually humans would read these zip codes, right? So a letter would come up in front of a human, and the human would look at it and type the zip code, 92373. Another one comes up, number. Another one comes up, number. Another one comes up, number, and so on. And so the idea was to have that done in a machine translation way. And as I remember, this was around 2000, okay, within a few years of 2000, so early on in neural networks. And what happened is the digits themselves were separated using some vision techniques. So what you ended up with actually is something like that. That you had to look at and say, what number is that? So it's a classification problem. Given a bitmap, decide whether it's the number 0 through 9. So this is MNIST. The input was 28 by 28 by 1. Right? It was black and white. And so therefore, we had some kernels, which were 3 by 3 by 1. How many of those were there? 32 such kernels. And so therefore, the output was 26 by 26 by 32. Now, these two numbers don't match, of course, 28 and 26. So what does that mean? That means these kernels used 0 padding. So we take these 26 by 26 by 32 and feed them to a ReLU. That's again then a 26 by 26 by 32. What we do now is we just do one Convolutional ReLU and we follow it by a pooling operation. So the pooling operation takes us by 26 by 26 by 32 to 13 by 13 by 22. At that point, we do another convolution. So we're going to have here a convolution that's going to take us down to an 11 by 11 by 64. So what does this tell us? How many kernels do we have? We have 64 kernels, right? That comes in here. Just to make sure we agree. So this 32 matches with this 32, right? We have 32 kernels, and so therefore the depth of the next layer is 32. This 1 here matches this 1. So that tells us each convolution was a 3 by 3 by 32. And we had 64 such kernels. And this 32 is that 32. And this 64 is that 64. Clearly, again, we have 0 padding because we are losing 2 pixels, height and width. After the convolution, we can do a ReLU. From the ReLU, we can do a pooling to 5 by 5 by 64. So going from 11 by 11 to 5 by 5 means we're actually losing the right edge and the bottom edge. And from this pooling, we can do another convolution. This convolution will take us down to 3 by 3 by 64. So again, we have 64 kernels at this level too. So we've got 3 by 3 by 64. Eventually, we need this classification problem, right? Eventually, we're going to need a softmax layer of size 10. And so let's go and look and see how that's done. Before we go there, let's actually look at each level and see the number of weights at some particular levels. So for instance, if we look at those, let's look at some particular layers and see what the weights are. So for instance, this ReLU layer, how many weights are there? None. ReLU doesn't learn anything, right? ReLU just does its thing. Nothing to be learned. Pooling, none. It's only the convolutional layers that actually have weights. Let's look at this layer right here and figure out how many weights we have. So we know we have a 3 by 3 by 32. That's for the kernel. We've got 64 kernels, and then we also have 1 bias for every one of the kernels. So let's just get an estimate how this is. This is 2 to the 6th times what? About 10 times 2 to the 5th. So that's around 10 times 2 to the 11th. 2 to the 11th is 2 to the 10th is 10 cubed. So that's around 2 times 10 to the 4th. So we have about 20,000 weights at this layer. And we could calculate then the number of weights at any given layer.